And first one is 10 milliliters of a 0.1 molar sodium hydroxide is added to 10 milliliters of a 0.1 molar bromide, and it should have been HBr. I could just got bromide in there. Sorry, just noticed that. At the equivalence point, what is the concentration of the salt? Okay. Okay, so we have a 0. Check that again. 10 milliliters of 0.10 molar sodium hydroxide. I'm sure this will be an aqueous solution, plus 10 milliliters of 0.10 molar HBr aqueous. After they've completely mixed and the reaction is dead, how much salt is present? Well, in working a problem like this, and you'll see this many times between now and the end of the semester, we're talking about mixing solutions. How do you evaluate solution data? Solution data is a volume and a concentration term like this. And the issue is how to translate this to moles and then relate to reaction. So this is the essence of what I'm trying to teach you right here, so that you can get it to moles and relate it to the reaction. The reaction here is sodium hydroxide and hydrobromic acid, double replacement to produce sodium bromide, and a little bit of water. The equation itself is balanced and shows a 1-to-1 reaction ratio. So the moles of NaOH is equal to the moles of HBr in neutralization. So, and also in here, at neutralization, would equal the moles of sodium bromide generated. Now that's strictly from a molar standpoint. This is a mass relationship, mass relationship, like that. It's not necessarily a concentration relationship. Concentrations, you recall, is dependent upon a volume after mixing. Not just the moles, it's moles per volume. Okay? In this particular case, we had 10 milliliters of 0.1 molar sodium hydroxide. Moles, as you recall, is molarity value given times the volume value given, and you can express it, should express it in liters if you don't have any more than calculate moles. Now, if you have an equation like this, you do not necessarily have to convert to liters, because molarity times volume of the acid equals molarity times volume of the base. Molarity times volume of the acid equals molarity times volume of the base. Well, the volume on both sides has equivalent units. See the point? And you don't have to convert that. But this is the exception rather than the rule. The rule is, if you get confused on what I'm saying, go for the change it all to liters. Molarity times volume in liters, well, doesn't matter. You'll come out right anyway. Okay? Okay, so here we have a 0.10 molar solution times a 10 milliliters, but I'm going to go ahead and go to moles because I want to show the relationship. 0.01 liter of sodium hydroxide is added to 0.10 molar and same volume, 1.01 liter HBr. Well, multiplying this together, we get a 0.001 mole of NaOH reacting with 0.001 mole of, that says mole, believe it or not, mole of HBr. So this is equivalent amounts in the equation. 0.001 mole reacting with 0.001 mole will in fact produce 0.001 mole of the sodium bromide. That is true. However, it is not the concentration of the sodium bromide at the end of this. To get concentration, and that would be brackets sodium bromide, and the emphasis is the brackets indicate molarity. And this will be used consistently throughout the entire textbook in this context. Okay. And is moles solute divided by volume of solution expressed in liters. Okay, by definition. So in this problem, we apply the calculation, molarity times volume of moles, 0.001 mole of sodium bromide, and we have 20, 0.020 liters, and that gives us a 0.05 molar solution in sodium bromide aqueous after mixing. And since I've mixed equal moles, I'm going to have total neutralization. If one of them was in excess of the other, this is important, then one in excess would be left over, and the other one would be the limiting reagent. Okay. Very important concept. If you struggle with this, please check mark this. Make sure you understand it. This is not the only time you will see this. You'll see it many times more. The points of issue here are, how do you convert solution data to moles? Because moles is what you're going to relate to the chemical equation. That's the essence. Because the primary calculation from a chemical equation is moles. And when I first introduced calculations and stoichiometry of chemical reactions, and we talk about using moles in the relationship, and as well as other mass values and data, I say the rule is convert to moles, apply to the reaction. After that, then if they want something else, you convert back. Work the problem in moles. Take the data, convert it to moles, okay, and then back to whatever they're asking for. They're asking for grams, you just multiply times formula weight or whatever they're looking for. And then you'll be back to grams. But work the problem in moles first, and then proceed on to whatever's next. Easier to probably emphasize the issue. B choice on that first one. Okay. Now the second one says 20 milliliters of 1 molar HCl is used to neutralize a sample of strong base, say sodium hydroxide. How many moles of base were used? Well, this is an emphasis on how do you convert solution data to moles. And in this context right here, moles is equal to molarity times volume expressed in liters. So in this particular case, moles would be molarity, 1 molar from here, times 0.020 liters from right here, and the outcome is like 0.02. Yeah. One times 0.02 is still 0.02 mole. Okay, so that would be D choice right there. Molarity times volume is moles. Molarity times volume is moles. I tell you that 100 times. You need to get that related to the equation early now, because we'll be doing it a lot. Okay, I'll just leave this up here. That kind of worked out pretty well. Let's see what we got here on number 3. In a titration, when sodium hydroxide is added into a solution of HCl, the limiting reagent is which of the following before reaching equivalence point? And I gave you the reaction. Now I may need to back up and draw some pictures here. Okay, number 3 here. And I've done this several times already, and I don't think it is overdoing it to do it again. The problem specifies that you are adding sodium hydroxide aqueous solution into a specified volume of HCl aqueous solution. And they want to know what the limiting reagent is before you get to the equivalence point. So if we have base, I like to make base blue. Anybody know what color litmus paper you use to test a base? Red litmus. Because it turns blue. Okay? Red goes to blue. What color do you use to test acid? Red because blue because it turns red. Yeah, it is kind of funny, isn't it? Okay, I emphasize this because of its importance. Such a degree here, to such a degree, it's going to be used from here on, because you want to be able to recognize or translate data that you obtain from this part of the equipment into what you've done down here and how these two relate. This is a reactant. If you're using sodium hydroxide plus HCl, you are looking at whatever the outcome of mixing those two are in here, and you want to be able to define quantitatively what's going on. So as we add some base here, the acid is converted into a salt. That's what the reaction is telling you. And so as we continue to add base, we'll continue to put salt in. And we add some more base, and it'll continue this neutralizing the acid, and the acidic keeps going down. Now, in putting the sodium hydroxide in, it is in the presence of an extremely larger amount of acid. So the definition of limiting reagent is that reagent which disappears first, okay, in a reaction. It's the one in the lowest reactive stoichiometry, because you'll have a lot of acid left over. Once that one goes away, what's left over doesn't have anything to react with, and consequently it goes to the salt. I got to do a better job of synthesizing salts. I can even see them. And so as we continue to put the base into solution, there comes a point at which all of the acid in here has been neutralized. Before neutralization, the limiting reagent is the base. At neutralization, neither one of them are present in the solution. Okay, you hear me? Neither the original acid nor the original base are present. What's left in the beaker? Salt. That's all that's left in the beaker. So once you reach the equivalence point, then the only thing you have in the beaker is salt. Beyond that point, you add another base in there. It does not have anything to react with. And so all you have is a solution with excess base, and that will be demonstrated in a titration curve with a higher pH. In this process, if you monitor it, as you add volume of NaOH as a reagent into the reagent and the beaker, the pH will alter. You have in here a monitoring device, pH meter, okay, pH electrode, and before starting the NaOH, you're going to be in a very acidic range. And as you add the base, it's going to be neutralizing the acid in here. And at very close to that equivalence point, there would be a rapid increase in pH. And that will eventually slow to something that approaches 14. Well, the equivalence point is right there in the middle of the inflection point, right there, and this is the volume, what we call the equivalence volume. The volume of base that we need to completely neutralize the molarity of the acid given is this point right here. And you can calculate that using molarity times volume equals molarity times volume, acid against base. For this right here, molarity times volume of the base equals molarity times volume of the acid. And so if you know how much you have here, we've been using 25 milliliters in our work of the acid. So you had 25 milliliters, and you don't know what if you have an estimate like a 0.10 molar, and 25 milliliters of that acid, you can guesstimate or figure how much of the base will be needed if you know its molarity, say 0.05 molar hypothetically. Matter of fact, when you do your experiment today, I would suggest that you use 0.05 molar, dilute down to 0.05, 20 to 1, instead of 10 to 1. Why? Because this will give you more points in here to be able to get more points. It won't gut through so fast. When the concentrations are very close together, when you start getting up close to that equivalence point, it'll go real fast. But if you have a lower concentration going in, that inflection will move slower. It won't change so fast. Everybody get that? So if you were adding, say, if I were doing this, I'd go 0.05 molar here, and maybe an HCl. I'd try to get close. I'd be trying to prove whatever my solution preparation was. And that's what the purpose of this is. You make a solution prep and then titrate it with a known sodium hydroxide. That's what calibration is all about. To prove what you've made. And it might come out in reality 0.98 molar. If you're trying to do very accurate and very fine work, it is critical that you make sure you know without question what the concentrations of your reagents are as you work with them. Okay?
Excuse me?
Okay, we're adding. The NaOH is a limiting reagent. Looks like a choice in our collection of answers. There, so magic changes itself. Yeah. Only salt here when you get here. Are we catching on? Everybody good? Very, very important, guys, because I want you to be able to look at an experimental apparatus and say, oh, okay, that's how much we need to put in. Rock and roll. And this is a very important concept. Okay. And the titration curve that you're looking at, where in this titration curve is the lowest concentration of acid? It's at the equivalence point. It's 0. That's a technical word, right? Because as you go through the titration, remember, at the equivalence point, there's no acid and base or anything down here. So 0, I don't think you can get less than 0 acid and 0 base. It's all salt. Everybody okay with that?
Well, there was none at A as well.
It's not a what?
There was no acid at A as well.
Yeah, that's true.
Okay. Point D is the highest concentration of acid. How do you know that that's an acid that we're looking at? pHs run from 1 to 7 or somewhere in there. Anything from below 7 is an acid. Everybody good there? If we're at neutral, this would be 0 acid and 0 base, only salt. The C region in here indicates that you have an excess acid. And see how the pH is increasing? This means that you're adding base to neutralize some of the acid. And since you don't have as much acid in the solution down here, it's going to start moving up toward the base range. And you start killing the acid, so to speak. So you have excess acid, but adding OH, but the OH is being converted immediately with whatever it comes in contact in equivalent amounts to salt and new water if you want to do that. When you get to here, the equivalence point, right here, you have 0 acid and 0 base, and it's all salt. There ain't no reactants left in there. It's just the salt products out and new water. In here, any additional base added is just excess NaOH or base. Because once you pass above this equivalence point, this 7 right here, anything above 7 pH is classified or defined as a basic system. Base system, alkaline system, however. Now, the reason it goes basic, it doesn't have anything to react with. The salt is not going to react with the base in this context. And so you continue to add base, it's just going to continue to give you a higher and higher alkalinity. Lowest acid concentration would be right here at B choice. B choice. That's at the equivalence point. I loved it. Okay. What you got up here? All base. Yes, no? Okay. What you got here? Acid. Okay. When this comes into contact with this, we have an NaOH reacting with, say, an HCl, okay? Producing an NaCl plus H2O. Before you add, now you've got a pH meter electrode in here. Before you add any base, what's your pH? Whatever it is on a strong acid, whatever that solution will give you. Okay? And acidic, here's your, say that's your 7. Here, most strong acids run about 1. Okay? So when we look at the diagram, this point right here is before you add any base at all.
Yeah, but that's D. I was talking about A.
I'm getting to A.
Oh, okay.
Up in here, once you get to, you keep adding that base. Let's see, am I still going? Let's see, I'm still going here. Yeah, I'm still going. Once you start adding that base, you start canceling out the acids down here. And I think you understand that. We keep going, and the pH keeps coming up, and then at some point in here it will go right up through here and right on over. Now what you're concerned about, I think, is the acid and the base right here, and you're telling me the acid at here is equal to the acid here? All right, what are you asking me on that content? In this region, I was thinking about it as an excess in terms of the base going in. If you mark, that's a good argument. Next time I construct the question, I'll make sure I work around that. But my emphasis was supposed to be the equivalence point.
So it won't be wrong then?
So, huh?
It won't be wrong then?
I would agree with you. You know, I would try to agree with you on that. Does everybody understand? You know, I wasn't thinking in terms. I was thinking, where is it the lowest concentration? Well, it decreases all the way up to here, and at that point, it's the lowest concentration. But it's also the same back in here. It never changes from that point on. But I was thinking in terms of the equivalence point, and this was where HCl equals 0, say, begins. Good argument. So, what can I say? Because of the way the question was worded, I will concede to that. Okay? Good point. Okay, and number 5 is easy enough. When a strong acid is used to titrate a strong base, the equivalence point pH is always what? 7. That's right. You will learn about an issue called hydrolysis. In this strong acid reacting with a strong base, we have no hydrolysis occurring. Therefore, pH is 7. If you have hydrolysis taking place, might as well learn about the facts of life right now. You have hydrolysis taking place, your pH is not going to be at 7. And you put an acid and you put an amount of base in with a weak acid and a strong base, the pH is going to be above 7. Listen to me. Anybody's texting their boyfriend or using something besides my attention, please stop it. It's rude. You think you know everything? Fine. Act like you don't. If you put a strong base on top of a weak acid, it's going to be acidic at the equivalence point. Learn these now. And this is at equivalence point. This one, your titration curve will be a 7. For the second one, your titration curve will kind of slope up a little bit higher and then go up here, that will be greater than 7. That's your acid base, weak acid, strong base. And then you would have a low pH, less than 7, pH greater than 7, so it's your right there. This is a weak base, a strong acid. This is a strong titration. The salt that's generated in these two will shift the pH. The salt is called salt hydrolysis, and you're going to learn about that in due time. But what's important is that you learn now how to evaluate the data that comes to you, molarity and volumes, and then translate it into that. Okay? What I want to work on now is a problem that I asked y'all to take a look at online.